The concept that molecules have three-dimensional shape is a very important one, both in chemistry and also in biology. We find that many of the small covalent compounds we're talking about have important biological roles, and the fact that they have a particular shape means that they can often fit like a key into a lock in larger molecules and cause biological changes through the change in chemical shape of other molecules. So we're going to look at one particular model for predicting what the actual shape is of a small molecule, and this is called VSEPR theory. So VSEPR stands for valence, shell, electron, pair, repulsion. What this means is that it's basically stating that the valence electrons, remember these are the ones that are involved in making the covalent bond, are always found in pairs. Either they're a shared pair, one electron from one atom, one electron from another atom, that are being bonded together. And they're going to repel because they have like charges. Each electron pair is negatively charged and wants to be as far away as possible in three-dimensional space from all of the other electron pairs that are on a particular atom. So to repeat, bonded and lone pairs. Remember, the lone pairs are the pairs of dots that aren't being used in a bond. Seek to move as far apart as possible. So what we're going to see is that the number of bonds plus the number of lone pairs on the central atom is going to dictate the shape. It's going to dictate the shape of the molecule. Okay, so let's see what that actually looks like. Alright, so what we're going to do is, for each of these shapes, I'm going to give you a shape. I'm going to give you the bond angle between the bonds. And then we'll determine how many bonded pairs and lone pairs will give you that shape. And then we'll give you a couple of examples and draw them so you can see this. Okay, first note for yourself is that if there's only two atoms, it's always going to be a linear. That's our first shape. I should say two atoms. That means that the two atoms are going to be in a straight line. Okay, so usually we only talk about shape if there's a central atom and at least two other atoms attached to the central atom. However, there's a lot of molecules that are just made up of two different atoms, and that's it. Okay, so like oxygen gas is two oxygen atoms. Hydrofluoric acid is a hydrogen and a fluorine. Okay, they don't have any others, but they're always going to be linear. So that's the first thing to remember. Alright, so our first shape is the linear shape. In this one, the bond angle is 180 degrees. This is going to be two bonds, 0 lone pairs. Okay, so there's no lone pairs, and there are two bonds on the central atom. It will be a linear molecule. So let's look at a couple of examples. The first one we're going to do is beryllium fluoride. So if we draw the Lewis dot structure for that one, here's Be. Okay, Be has two dots, remember? And then we're going to draw, here's the two fluorines. Each fluorine has 7 dots. Okay, so if we look here, we've got one bond here, and we've got one bond here. Now even if I drew one of the fluorines here or one of the fluorines here, it's still two bonds. The difference between a Lewis dot structure gives us some idea of how the molecules are bonded together, and we can use it along with our knowledge of VSEPR theory to predict the shape of the molecule. The Lewis dot structure doesn't always show the actual shape of the molecule, and it really does not require that it does. And if you get very used to the VSEPR theory after a while, we tend to draw automatically the Lewis dot structure so that they obey VSEPR theory. But it's okay if your Lewis dot structure doesn't match exactly what you said is going to be the shape. Okay, just as long as you can figure out what the shape is after you draw the Lewis dot structure. Okay, let's do another example, because this points out something very important. Okay, let's do carbon dioxide. Alright, here's carbon. Carbon has 4 dots. Here's one oxygen. I'll put the other oxygen over here. Remember, I'm trying to make the molecules symmetrical. That's always a good rule of thumb to follow. Okay, and I'm drawing the single dots, remember, close to other single dots so that I can put this molecule together correctly. Alright, so carbon and oxygen connected. Single dots are always connected on two adjacent atoms. So this is essentially, if we look at this, this carbon is double bonded to this O and double bonded to this O. Now, in VSEPR theory, this is an important note for yourself. Note. If you're trying to count the number of bonds, count double and triple bonds as one bond. That's really, really important if you're trying to remember how many bonds go along with what shape. So do not count this. Don't say this is 1, 2, and this is 1, 2 for a total of 4. This is not 4 bonds. This is one double bond, a second double bond. So there are 2 bonds on the carbon. So this is also a linear molecule. Okay, 2 bonds. You notice that there are no lone pairs left over on the carbon. Okay, let's go to our next shape. Next shape is called bent. Okay, the bond angle for a bent molecule is less than 109 degrees. Okay, it's going to have two bonds. And the number of lone pairs is either 1 or 2. 1 or 2 is going to give me a bent molecule. Okay, so what's a good example of a bent molecule, and what do I mean by this less than 109 degrees? Well, let's use, for example, water. Water's a great example of a bent molecule. Let's put together the Lewis dot structure real quick for water. Here's O. Let's put my H's. Okay. Now, when we're talking bond angle, it's important for you to know that this is the angle between the bonds in the molecule, not the angle between the bonds and the lone pairs. But here's another important note. That lone pairs repel more than bonded pairs. So if I could actually measure the angle between the bonded pair and the lone pair, I discovered that this is smaller than the angle between here and here, which means the lone pairs basically need more room. So they push these two bonds a little closer together. And so the bond angle here is a little less than 109 degrees. Now, exactly how much less depends on if there's one or two lone pairs over here on this molecule. Okay. Having one lone pair and two bonds is a really, really rare occurrence. Two bonds, two lone pairs, something like water, is a much more common occurrence. Okay, let's look at our next one. Okay, our next shape is called trigonal planar. Trigonal meaning a triangle, and planar meaning in a flat single plane. The bond angle for a trigonal planar molecule is 120 degrees. The number of bonds is going to be 3. And the number of lone pairs is 0. Okay, let's look at a couple of quick examples of that. Let's look at aluminum trihydride. Now this is an important point where, like beryllium fluoride, when we put together our Lewis dot structure, it doesn't always give us an accurate picture of the shape of the molecule. So we can't always just rely automatically on the Lewis dot structure to show us the correct shape. We're going to have to remember what VSEPR theory says happens. Alright, so we're going to put this together. Alright, so here's our molecule. Okay? And remember, each one of these bonds is going to want to be as far apart from each other as possible. If you look at them right now, these two bonds are drawn 180 degrees apart from each other, and these bonds are drawn 90 degrees apart from each other. Okay? These aren't anything special about these two hydrogen bond, aluminum bonds here. So we're not going to see this shape. We're going to see trigonal planar, which means that they're going to try to get equally far apart from each other, which is 120 degrees. So the actual shape of this looks really like this. Okay, so the way this is now drawn, these angles should be all equal and they should all be 120 degrees. So it really does look, if you kind of drew a little outline here, okay? The molecule really is kind of in the shape of a triangle, so that's why it's called trigonal. Don't call it triangle. Trigonal planar. Okay, on to our next shape. Okay, our next shape is tetrahedral. Tetrahedral. Okay, the bond angle for a tetrahedron is 109.5 degrees. The number of bonds on our central atom is going to be 4. And the number of lone pairs is none, 0. Okay, so a good example of this is CH4. This is another example where the Lewis dot structure gives us clues, but it's kind of misleading to the shape of the molecule. Okay, if we look at this molecule right now, it looks like these 4 CH bonds are as far from each other as possible. If we look at it, we can probably guess that these look like they're about 90 degrees apart from each other. So it looks like these form like a square or a diamond. The reality is that there's a different way for it to be drawn that actually gives a larger bond angle. And that's what we call the tetrahedron. Okay, now this isn't going to look very much different at first. Okay. Okay. This little dash thing means it's going back, like through your computer screen and out the back. Okay, and when we do this, okay, it's actually ends up with a larger bond angle because molecules are not flat. Molecules don't have to be flat. They can move in 3 dimensions. So these two H's come forward a little bit and this H moves back. Okay, we end up with what looks kind of like a tetrahedron. Okay, down here on the bottom, it's called, you have like a triangle and then it goes way up here. This is called a tetrahedron. So if there's 4 bonds, it is a tetrahedral molecule. Okay, last shape. Okay, our last structure is called trigonal pyramidal. The bond angle for this one is 107 degrees. Okay. The number of bonds will be 3. And the number of lone pairs apologize for that, will be 1 lone pair. Okay, So a great example of a trigonal pyramidal molecule is nitrogen trihydride, NH3. Okay, so let's put the Lewis dot structure together for this one. Okay, so this one at first glance looks a lot like trigonal planar, except we've got this extra lone pair here. So the lone pair here is going to push these hydrogens down and away from each other. Okay, so it's actually going to form a structure that has a triangle base, okay, with nitrogen up here at the top and the lone pair sticking out the top. So it looks like going to look just like a pyramid, with nitrogen up at the top and then hydrogens at each of the three base corners, but it's a pyramid with a triangle for a base instead of a pyramid with a square for a base. That's what we call trigonal pyramidal. Again, 3 bonds, 1 lone pair. Okay, the very last thing that we're going to mention in here is an important concept. It doesn't directly affect shape, but it is the last important concept in Lewis dot structures, and that is resonance. Resonance occurs if a double bond can be drawn in more than one possible location. Okay, so to show you that, let's go back to SO3. This is one of the ones I showed you as an example for Lewis dot structures. Okay, now remember that SO3 is drawn to get the 3 oxygens on. We get 1 oxygen here, and remember this oxygen is going to make a double bond, and in order to get the other O's on, these other oxygens are going to have to steal a pair off of the sulfur. So you're going to get one of the O's will be here and one of the O's will be here. And remember, this is the I'm stealing a pair off of you to make our single bond Lewis dot structure, Lewis dot symbol, excuse me, for oxygen. Okay. Now, I didn't have to draw the double bond on this side. I could have drawn the double bond up here, and I could have drawn the double bond up here. Now remember we mentioned that double bonds are both stronger and shorter than single bonds. Scientists have ways to measure basically the distance between the center of the nucleus of the sulfur and the center of the nucleus of the oxygens. And so we would expect that this distance would be a little shorter than these distances. However, when they look at a molecule like SO3, which has both SO single bonds and SO double bonds, what we actually end up with is something, what they can measure is 3 bonds that appear to be exactly the same, and they're sort of in between the distance for an SO single bond and the distance for an SO double bond. So the explanation they've come up with is that this double bond actually just moves around from place to place. It kind of jumps from place to place. Okay, it's not the oxygen atoms are jumping, it's kind of the bond is here and then the double bond structure moves here and this becomes a single bond and around and around. So that's what we mean by resonance. Okay, it's actually a moving double bond. Okay. And the net result is just you get something that's kind of in between a double and a single bond in all 3 places at the same time. It may sound a little unusual, but remember we are talking about the behavior of subatomic particles, namely electrons. Remember, these don't behave the same way as apples falling from a tree or a ball rolling across the ground or anything like that. Okay, subatomic particles obey a different set of rules. Okay, so the only thing you're going to have to know, is what is resonance, or if I ask you to draw a Lewis dot structure, I'll ask you to identify a Lewis dot structure if it contains a resonance or not. If you look at your Lewis dot structure and you say there's a double bond, and I could have drawn the double bond in a different spot and still have it be a perfectly reasonable Lewis dot structure, you can say that that particular molecule exhibits resonance.